All right, so we're recording. Bye. All right, cool. What else? All right, well, let's hop over to the ODPs. So the ODP that was due yesterday was looking at this question of, let's see if there's a command line argument and do something differently based on whether there is or isn't. And so my sample code S1, if you run it without a command line argument, it gives you this simple prompt, waits for a number, and then prints out twice the number. And if you run it with a command line argument, it just prints out twice that number. And there's different ways you can do that, but here's a pretty straightforward way. So in this case, I set num equal to whatever the first argument is. And I said, if that first argument is blank, then let's, ask the user to enter a number and read num. And I structured it like this because the way I was thinking about this, sort of from a flow, is set num equal to user number, and then print 2 times num. And this to me was a simpler version of this ODP than something like the following. If arg given, print 2 times arg. If no arg given, prompt read number, print 2 times the number. Now this will do exactly the same thing, right? I could check in the beginning to see if $1 is not blank, or see if $number sign is equal to 1. And if that's the case, then I just print 2 times $1, and I'm done. Otherwise, I'll print out a prompt, read a number, and print 2 times that number. But the way I chose to write this was the beginning of my script. Its purpose is to get the number that the user wants to work with. And I can do that 2 ways, right? If an argument is given, this will set num equal to that argument. If a number is not given, this if statement will be true, so I'll prompt and then read a number from the user. And then once I get down here, by whatever means necessary, num is now equal to the number the user entered, and so I can just print 2 times num. So you can structure these things a number of different ways, but for PA3, for example, we want to get the number of sticks the user is playing with, and that can come through a command line argument, or it can come through asking the user how many sticks and then doing a read statement. And then in either case, we want to see if that number is bigger than or equal to 5. And if it's not, we're going to print an error and just exit. And rather than doing that checking and exiting, twice, I can do it once if I just make the top of my script something that decides how many sticks the user wants to play with, and then check the legality. So whatever way you decide to implement this, that's really what this was about, for sort of exploring that idea of being able to work with one of 2 startup conditions, either command line argument or asking the user explicitly for a number. And then ODP 406 is another script that will probably help with PA3. And this is a script that just, takes a number and outputs that many pipes followed by the number in parentheses. So it's not a drop-in piece of code for PA3 because we don't ask the user, how many pipes should I print out? But you have a variable that you're using throughout the game to track the number of sticks. And so if you use that variable instead of, something you get from a read statement, you can print out this picture of the sticks the way we need. And again, you're not allowed to use for loops in your bash programs. So you've got to structure this loop with a while statement. And a while statement is just initialize some index. And if we want to do, 5 times, we can echo our pipe character with a -n, which says don't print a new line at the end. Increment our loop and then say done. And that prints out our 5 pipes side by side. So that's a for loop basically, but it's coded with a while statement. So any questions on either of those? Everybody okay with how to do the next ODP?
The next one being like this one you just were talking
Yeah,
about?
this one we just looked at, 406.
Oh, okay, cool. Yep. Thank you.
Cool. All right, well, let's go on. So I posted PA4 a few days ago. And let's pull up the PDF for that. So PA4 is another game. It's going to be a bash script, and it's the game of high-low. And so this is a guessing game. And the way you play high-low, if you haven't done this before, one person thinks of a number and the other person tries to guess what the number is. So pretty basic game setup. Now, if I think of a number between 1 and 100 and you just start making random guesses, it could take you 100 tries if you're really unlucky to guess my number, right? I might think of 17 and that might be the last number you guess. But there's a way that we can control our guesses to do a lot better than 100 possible guesses. And in fact, if you think of a number between 1 and 100, somebody can guess it in 7 guesses or fewer. And so instead of just guessing, is your number this, is your number that, after someone makes a guess, the person who thought of the number indicates whether the guess is too high or too low or correct. So I might think of a number and somebody would say, okay, is your number 10? And if I'm really thinking of 25, I would say, no, 10 is too low. And then they might guess 60 and I'd say 60 is too high. And the idea is we can narrow down what their number is if we make appropriate guesses. Yeah, so question in chat on PA3. Yes, so if you're running the stick game, so let's play with 200 sticks. So I'm not going to say something like, ha ha, I'm not going to say something like 2.4. I'm only going to type in an integer, but I might type an invalid integer like 0, in which case you should say pick a number between 1 and 4. Or I might say I'm going to take all 194 sticks. Just say no, pick a number between 1 and 4 and make sure the entry is in range. So you don't have to check the syntax of the entry. You can assume it's an int, but yes, make sure that it's between 1 and 4. And in starting the game, if you put an argument on the command line, right, you don't have to worry that they're going to say haha or 20.3 or 20 haha or something like that. You can assume if they put an argument, there's exactly one argument and it's an integer, and then go ahead and play with that many sticks. I'm not going to play with 1,999 sticks. Actually, I can have it play automatically.
Are we ever going to be doing any, I'm thinking, any error, input checking?
For Bash?
Yeah.
You may want to do some on PA5 when we get to that. We're not really doing it for PA4. We're not doing it for PA3. And in that Bash handout on Canvas, the how-to guide, there's a little blurb at the end on some ways to do error checking. But it's not a terribly clean thing, and I don't think it buys us a lot to get bogged down with that. And there's better ways to do it once we understand regular expressions. But for now, yeah, we're just going to ignore it. But you can do it. Hey, I won the game. Cool. So there's a command called yes. And if you say yes, it just says, a bunch of Y's forever. If I say yes, followed by anything, it'll just repeat that anything forever. So I can just have it say no. And so to play my really long stick game, I just said yes 4, which just keeps printing out the number 4. But instead of printing it, I piped it into stick 2000. Well, stick 2000 reads from standard in. And so it keeps reading a 4 when it asks me how many sticks I want to take. And that's how I was able to get through this big long game. So I just kept taking 4 sticks. And yeah, the algorithm is that it always picks 1 if the number of sticks is a multiple of 5. So I know that I can always pick 4. But if you threw in a little random factor that sometimes would pick 2, then yeah, you'd trip up these automatic bots that try to beat your game. So that would be cool. But don't do that. All right, so yeah, so PA4, so high-low game. So the idea is we're going to not just make random guesses, we're going to control our guesses in a very specific way. And the basic idea is, let's say that we're playing high-low between 1 and 100. So user is thinking of a number between 1 and 100. So before we've done anything, all we know is that the number is somewhere in this range. And so the user makes some initial guess. And suppose we guess 50. Well, if that's the number that the person was thinking of, hey, we lucked out, we guessed it with only 1 try. But chances are that's not the number they're thinking of. So if they tell us that 50 is too high, we know that 50 is not their number. We also know 51 is not their number. Neither is 52 or 53 or 75 or 99 or 100. If 50 is too high, we know that their answer, the number they thought of, was something between 1 and 49. And if 50 was too low, then we know they're not thinking of 50, they're not thinking of anything smaller than 50, they're thinking of something between 51 and 100. And so with just a single guess, we've taken the original problem of trying to guess one of 100 numbers and reduced it to guessing one of 49 numbers. So our problem is twice as simple in some sense. There's only half as many numbers that we have to choose from. So the user is trying to guess the computer is trying to guess the user's number. So user thinks of a number, computer is guessing. So if we know the numbers between 51 and 75 and 100, we'll pick a number in the middle and say, is the number 75? And if that's too high a guess, then we know the number is somewhere between 51 and 74. And if 75 is low, then we know the number is between 76 and 100. If the number is between 1 and 49, we'll guess 25. And if that's too high, then the number's got to be between 1 and 24. If this is too low, the number has to be between 26 and 49. And so roughly speaking, you know, we went from 100 possibilities up here down to 50 possibilities here, down to 25 possibilities here. And so each time we make a guess, the size of the problem shrinks. In particular, it gets cut in half. Now, if someone says, hey, I'm thinking of a number between 7 and 7, you can guess what the number is. It's going to be 7. So if we can shrink this original problem from a range of 100 numbers to a range of just one number, then we can always get the answer correct. We can always figure out what number they're thinking of. So if we start with 100, we make one guess, we'll come down to 50, 25, 12 or 13, 6 or 7, 4, 2, 1, right? Eventually, we're going to get down to where we know that the number is, you know, between X and X. And then we're just going to say, oh, I guess the number is X. And this is a really powerful concept in programming, this idea of taking a problem and breaking it into smaller problems. This is something called divide and conquer. And it's a general class of algorithm that does exactly this, takes an original problem and breaks it into a smaller subproblem, reduces it to a simpler question. And when we're dividing by 2, that's really powerful, because cutting things in half gets us down to 1 pretty quickly. So it turns out if we're guessing a number from 1 to 100, it's going to take 7 guesses, worst case. 1 to 1,000, 10 guesses. 1 to 1,000,000, 20 guesses. 1 to 1,000,000,000, only 40 guesses. So think of any number between 1 and 1,000,000,000, and your program should be able to guess it within 40 guesses, which is pretty remarkable. And when we use computers to do useful work, it's usually not, you know, having it try to guess a number we're thinking of, but it might be doing something similar, like searching for a piece of information. So if I have an alphabetized list of 1,000,000 names, and I'm searching for one name in that list, I can find that name with just 20 operations. which is a lot faster than just starting at the first name and moving through to the second, third, fourth, fifth name and comparing each name to what I'm looking for. That could take a million operations. And if the name's not in the list, it's going to take a million operations. If I do some kind of divide and conquer algorithm, I can accomplish that same task with only 20 operations. And so this is something we'll use a lot in CSE224. And someone asked a little while ago if this was like a binary tree. This is exactly how we deal with binary trees. This is why we study binary trees in winter, because they have this divide and conquer characteristic. And they'll be a key to taking large problems and making them solvable in short amounts of time. So it's a little bit about probability, but we're really not using probability a whole lot here. So we're pretty much just going to kind of blindly always make a guess somewhere in the middle of whatever range we're working with. And that may not be, most people aren't going to pick 50 if you ask them to think of a number between 1 and 100, because that's kind of obvious, right? So usually this is not the best guess we could make originally based on probability, but this is going to be a pretty uninspired algorithm. It's just going to do exactly the same thing every time. And so let me run through some sample execution of this, and then we'll go through the assignment and see all the details about error checking and so on and so forth. So your script's going to be called high-low, and by default, it's going to ask you to think of a number between 1 and 100. And it's going to wait for me to think of a number and then hit a key to start the game. So you don't want your program to just say, hi, let's play high-low. Are you thinking of 50? Right? You want to be kind of conversational here. You want to let the user think about a number first and say, okay, I've got a number in mind, and then I'll hit enter, and then it can say, is your number 50? All right, so let's say I'm thinking of the number 60. So 50 is too low, so I'm going to say that's low. It'll say, is your number 75? That's high. 62 is high. 56 is low. 59 is low. 60, that's correct. So I'm going to hit a C, and it says, great, I got your answer in only 6 guesses. So that's the basic behavior of the game. The other thing I can do is I can say high, low, and I can put in an argument on the command line, and it'll say, think of a number between 1 and whatever number I put in. So I don't know, I'll still think of 60. All right, so I got my number in mind, and it'll say, is it 500,000? That's high, 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 high. These are all too high. That's too low. That's too low. That's too low. There we go. And so I got my answer in 20 guesses. All right, does that make sense so far? Basic structure. Cool. All right, thumbs ups. All right, so let's look at the details. So the name of your script is high-low, all lowercase. And so to play the game, I can say high-low followed by enter. Print a welcome message, tell the user what you're doing. Ask them to think of a number and then wait until they hit a key. The user thinks of a number, hits a key, and then the program makes a guess and says, is your number 500,000? Okay, if the guess is correct, the user hits the C key and the game's over. Tell the user how many guesses it took, and you can gloat and make fun of the user for losing or whatever, and then just exit the script. If the user says it was too high, they're going to hit the H key, and you should make a new guess. If they say the answer was too low, by hitting the L key, you should make a new guess and continue. And you just keep going until the guess is correct. All right. The other way you can run the program is with a command line argument and then play between 1 and whatever argument. So high, low 1000, ask them to guess a number between 1 and 1000. All right, so details, it's got to be written as a bash script, and it's got to be bash in the style of our style guide, right? It's got to use the exact syntax and statements that are in that bash handout, including no for loops, double brackets on conditional statements, and so on and so forth. All right, code needs to be commented. You need a comment block in the beginning with your name, the class, the date, a description of the code in your own words. All right, next detail, we don't want the user to have to hit the enter key after they type a key. So when I'm playing this game, so let me do this. So there's my keyboard. And this is pretty awkward. So it says hit any key when you have a number in mind. So for example, I can hit the space bar and it will go ahead and say, is the number 500,000? If that's too low, I don't have to hit the enter key. I can just hit the L key and it gets that input and says, okay, how about this? And I can say that's high by just hitting the H and it'll go on from there. And I'll show you how to do this in a second. But this is a lot easier for the user than having to type H followed by enter or L followed by enter and so on. And remember, I'm gonna end up playing, you know, several hundred high-low games over the weekend. So if you can save me from having to hit enter each time I say H or L, that's gonna make my life a lot faster. Now, if you put in something that's not H, L, or C, it should say, hey, you know, put in an H, an L, or a C. So anything else that I type in, it should just give me an error message. And then an H is too high, an L is too low, and a C is correct. All right. So don't require the user to hit enter after typing H, L, or C. So how do we do that? There's a switch we can put on the read command. So if I say read -- help, I'll get this really not very detailed one-line description of all the options. Well, one of the options on read is -n, which says read this many characters. So if I say read -n1 answer, as soon as I hit any key, my read comes back. And the value of the key that I put is inside this variable answer. All right, so read -n1 will work for this. Now, we don't normally want to do this. If I say, what's your name? And I say read -n1 name, and I try to say my name is Nick, right? It's just reading the first letter and coming back. So this is not normally something we do, but for this case, we specifically want a single keystroke and we want to come back from the read statement. So we're going to do this read -n1. So any of your friends who aren't in class today, if you want to be nice to them, you can tell them about this. Otherwise, they're going to be asking about it later. All right, so that takes care of this requirement. We'll go over the algorithm in a few minutes. Your program should also detect cheating. So here's a situation. So let's play stick. And let's say I'm thinking of the number, sorry, not stick, high-low. So let's say I think of the number 50. All right, so, okay, I got a number in mind. I hit this, it says there's a number 50. Well, I don't want to be a loser, right? I don't want it to guess my number on the first try. So I'm going to say 50 is too low. Okay, and then these will be too high. And you know, no, I just don't want to lose. So I'm going to say, yeah, that's too high. Well, at this point, it knows that something went wrong because previously I said 62 was low. And just now it guessed 63 and I said that's high. So it said something's wrong. Did you forget your number? Which is a nice way of saying you're cheating. So as soon as it detects that you're cheating, it can just tell you and then just exit the game. And we'll talk about how to detect cheating in a minute too. All right, so that's the next requirement. It should detect cheating, inform the user if you notice it, and then exit the game. Name the script high-low, put it in a PA4 subdirectory under CSE224, push it to GitLab by the due date, which is a week from tomorrow. And then I'll download it that day and grade it. All right, so PA3 is due tomorrow morning. PA4 is due a week from tomorrow morning. So it's a 1-week assignment. And it's really no harder than stick. And since you've already written stick, PA4 should go very quickly. Different algorithm, but same idea of an infinite loop and getting information from the user and doing something based on that. All right, so things to be sure of. Make sure the user is thinking of the number and the program is trying to guess it. Don't flip those around, right? The computer does not think of a number. The computer tries to guess your number. Make sure that H means the guess was too high, L means it's too low. If you're thinking of 10 and the program guesses 50, the user should say H, meaning that's too high. And don't flip those around. Sometimes people get those backwards. All right, the program begins by asking the user to think of a number between, say, 1 and 100 or whatever the top number is. And it asks the user to hit a key once they've thought of the number. Don't just make a guess until the user's thought of a number and then hits a key. If you hit anything other than H, L, or C, print a 1-line message reminding them what the keys are and just ask them again. And you're welcome to, invite somebody else over to your laptop and have them try your game out. Don't send them your code, because if you send them your script, they can see the source for it, right? We can't compile it and hide the source. But if you want to have somebody else play your game to try to break it, you're welcome to do that. It's a good way to do, sort of final error checking. All right, I should also say in here somewhere, so if they put an argument on here, you can assume that it's a positive integer. And if they happen to type other things after this, you can just ignore those. So you're not required to handle the case where somebody says high-low, ha-ha, or high-low 2.777. You don't have to handle those cases, right? And you don't have to handle high-low -10 or something like that. So just high-low, if they put an argument, you can assume it's a valid integer and then just play between 1 and that number. If you set permission bits to execute but not read, you actually can't execute it. I mean, you have execute permission, but since you can't read the file, you can't get to the stuff that you need to in order to execute it. So that's unfortunate, but all right, so hey, it thought of my number. All right, so questions on that so far. We still have to go through the algorithm, including how to detect cheating, but questions on the basic setup, the gameplay, and so on. All right, cool. So let's look at the algorithm. So we're playing this guessing game. And originally we're told, think of a number between 1 and 100. So let's see. Why can't negative numbers be used? Yeah, you could do this with negative numbers. There's absolutely no reason why you couldn't. And it doesn't even change the code. So, I mean, more generally, I could say, let the user specify the lowest and highest number. And you could say, okay, I'm thinking of a number between -30 and +500. And you could play the game exactly the same way. But I'm just making it a little simpler. So low number is always 1. All right. So initially, we're thinking of a number between 1 and 100. And so we have to guess something in that range. But wherever we are, we need to keep track of what the possible range of guesses is. And this is going to change as we play the game. So originally, we're going to start off with low is 1. And if we're playing up to 100, high is going to be 100. So this is, smallest guess. And this is our largest guess. And it makes no sense to guess something smaller than 1 or bigger than 100. So our goal is to, take this original problem where we're trying to think of a number somewhere between here and here and split it into a smaller problem. Now, if I were to say, is your number right here? I could get lucky, right? So if these are the small numbers on the left and these are the large numbers on the right, and I say, is your number right here? I could get lucky and they could say that number is too big. And all of a sudden I can ignore all of this. And now I have their problem shrunk down to a really, really tiny problem. Their number is somewhere between here and here. And it's only going to take me a few guesses. But if I get unlucky and I say, is your number here? And they say that's too small, all I've done is removed this little tiny piece of the problem. And now I'm playing a game where I'm saying, okay, your number's somewhere between here and here. And I've only reduced the problem by a little bit. And what we want to do is guarantee that on average, we get the best possible outcome, the fewest number of guesses. And the only way we can do that is if we make our initial guess pretty close to the middle of this range. And now whether that's too high and our problem becomes this, or too low and our problem becomes that, our new problem is going to be roughly half the size of the original. So all things being equal, the guess we want to make is the average of high and low. So we can do low plus high over 2. And then we can say ask if guess is correct. Okay, if it's correct, then we're done. The program guessed the user's number. We can say thank you for playing and we can exit. All right. If the guess is too high, we guessed this number and the computer said that's too high. We know that the number is somewhere in this range. So the low end of our range hasn't changed, but the high end has changed. And the high end, instead of being over here, is now right here. In particular, the high end of our possible range of values is 1 less than the guess we made. Because we know the guess is not correct, and we know nothing bigger than the guess can be correct. So if the guess is too high, we can set high equal to guess minus 1. And then we can go back up to the top. Alternatively, if the guess is too low, then we can change the low end of our range to be guess +1. And then go back up to the top. So with bash, arithmetic is always done with integers. So if I say something like low equals 1, high equals 100, and then I say guess equals low plus high over 2, it's going to truncate. So in this case, it's going to give me a 50. Right? So it doesn't round. 1 plus 100 over 2 is 50.5, but it just ignores the decimal point and it gives me 50. All right, so this algorithm will work. And if you change this algorithm, it may work or it may not work. But I've given this assignment in the past, and about a quarter of the assignments come in and they're not using this algorithm. And most of the time the code doesn't work and there's point deductions. And I'm giving you the algorithm right here, right? Now you should try to understand this. And if you think that something else would work better, you're welcome and encouraged to try to do something else. But be absolutely certain that what you're doing works, which means you want to play your game 20 or 30 times with lots of different test cases, lots of edge cases, and make sure that it's actually doing what you think. But this is guaranteed to work, right? Set your low and high originally. And if they say, you know, some command line argument, set high equal to that, and then start off with your guess in the middle. Ask if the guess is high, then change your high to guess -1. If the guess is low, change your low to guess +1. And if you make this -1 or you just make a guess or something like that, it's not going to work, right? Computer science is super detail oriented. You use a comma instead of a period and a rocket blows up on the launch pad. So these details are critical. And the reason for these details is, you know, if the guess is too high, we don't have to try guess again. The highest we could possibly work is guess -1. If the guess was too low, if they guessed 25 and I said that was low, we don't want to guess 25 again. The lowest we'd want to guess is 26. So we said low to guess +1. All right, so that's the basic gameplay. We'll talk about cheating next, but any questions about this? So if you want to do an infinite loop, my suggestion is while space bracket bracket space 1 space dash EQ space 1 space bracket bracket. Because that's using the same syntax that we're used to. And you can do something like while bracket true, do echo hello done, right? But if I say while bracket bracket false, do echo hello done, well, that's also an infinite loop. So even though it looks like this is making a reasonable infinite loop, it's a illusion, right? Because if I say while bracket bracket false, that also loops forever. This is not doing what we think it's doing. And this is the whole challenge of working in bash, is it's so easy to do something that looks like it's doing the right thing, and it's really not. So I would say you should do this with something like while bracket bracket 1 equals 1. do, and then do the body of your loop and leave it like that. Or you could do something like that, because that will always be true. All right. Let's take a 5-minute break. We'll come back. We'll talk about how to detect cheating, and then we'll go on to some other Linux stuff. Let's see. When the user presses C, we break that infinite loop by saying break. Yes. So if the entry was correct, we can get out of this infinite loop by saying break, or we can just make an exit statement after we, say goodbye to the user. We can say exit, and exit takes you out of the entire script. So we can also get out of the loop like that. But yeah, break would be the more subtle way to just leave the loop and then go down to the bottom and continue. Cool, you're welcome. All right, we'll take a 5-minute break, and then we'll talk about cheating, and then we'll talk about something else. All right, let's see. How do we detect cheating? So cheating occurs when there's only one possible number left and the computer guesses that, and the user says, no, that's not right. So if there's only one possible number left, that means that low and high are going to be the same thing. Because if low is 15 and high is 16, well, there's two numbers left. And so the user might say, you know, the computer might guess 15 and the user could say that's too low. But when low and high are the same, that's it. We know what the number is. And if the person says that the answer is too low, then we're going to change. So we're going to make guess. So this is, you know, equal to our number. We're going to make our guess, which is our number. And if the person says that's too low, then we're going to change low equal to our guess plus 1. And low is going to be bigger than high. And if the person says that our guess is too high, then we're going to change our high to be our guess minus 1. And high is going to be smaller than low. So our error condition is when low is bigger than high after we've adjusted them. So the only thing you have to do to detect cheating is right up here at the top of the loop. If low is bigger than high, then the user is cheating. All right, but again, there's lots of ways you might think that you could do this. And a few of them may work, but most of them will not. So calling cheating when low equals high is too soon. Checking to see if low is bigger than high somewhere else in here may not work. Counting the number of guesses may not work. But just at the beginning of your loop, right after you've got the current value of low and high that you're about to make a guess on, if low is bigger than high, at that point you can say, hey, something's wrong, goodbye. Does that make sense? So let me show you how I'm going to play your game when I download it and try to grade it. So first thing I'm going to do is think of a number like 60, right? So I'll say that's low, high, high, low, low. Correct. And make sure it works, make sure it knows that it guessed it, make sure the number of guesses is correct, and so on and so forth. And then I'll play high, low, and I'll say, you know, 50, yeah, that was correct, and make sure it understands that's the right number. And then I'll pretend that my number is 1, and so I'll make all these guesses high, and it should get down to guessing 1. And then I'll think that my number is 100, and I'll make all these guesses low and make sure it gets to 100 and actually guesses 100. And lets me say, okay, that's correct. And if there's a problem with your cheat code, it may call cheating before I get all the way to 100. And then I'll try to do some cheating. So I'll just start saying that all these numbers are too high. And once I say 1 is high, it should say something's wrong. If it guesses 1 twice, there's a problem in your algorithm. And then I'll try and say that all these numbers are low. It should guess 100. If I say 100 is low, it should say, hey, something's wrong. And then I'll start off, you know, saying that the number's too low, and then I'll switch to too high, and I should get it down to 76. And then I might play with a number like 1,000 and think of a number 600 and make sure that it gets to that number. And then I'll look at your source code and look for comment blocks, look for how the thing is organized, make sure you use the types of bash statements that we want used and you didn't use for loops and so on. And that's pretty much it. Right. So, I mean, as you develop your program and as you get ready to make your final submission of it, you can do the same set of tests. Right. And there's nothing magic about this. There's nothing magic about the number 60 or something like that. But I'm really exercising the extremes. Right. When I do something like this and I just say, you know, all these numbers are high, it's got to get all the way down to 1. If I say this is high and it guesses 0, there's a problem in the algorithm. If I say this is high and it guesses 1 again, there's a problem in the algorithm. If I get down to this point and instead of guessing 1, it says, oh, you're cheating, there's a problem with the algorithm. So this is an edge case, right, where I'm forcing it to get down as far as possible before I tell it that that's correct. And then if I tell it that that's low or that that's high, it should say, you know, something's wrong and so on. So exercise your code as much as you can. Try as many different tests as you can. Now, having it guess 60 versus 70 versus 65, not really significant, right? If it works correctly when I think of 60, it's probably going to work correctly when I think of 65. But, you know, I'll do a few games where I just think of some nominal number, like maybe 70. And if it works for, you know, 2 or 3 numbers, it's probably going to work for all cases. So then the question is, what does it do on the edge cases, the extremes, including cheating? All right, so everybody got this? I'll mark this with an asterisk and keep this. All right, so that's PA4. And you can start it anytime you like. It's due a week from tomorrow. And like I say, it's really no harder than PA3. And having already done PA3, it should go quicker. I know some people finished PA3 in a few days. A lot of people have finished it already. 3 to the 7th is 2187. This is true. Yeah, but then I also want to, oh yeah, so other test cases, you know, I'm gonna definitely test some illegal entries and make sure that works and make sure after a few legal entries, it detects illegal entries and so on. So there's some more test cases. But most of those, yeah, like as soon as you say C, you don't have to test, you know, any of the cases after. So it's probably fewer test cases. So yeah, we could do it exhaustively. On the other hand, you know, you could, instead of writing the actual program, you could just look for each of those 2,187 input combinations and print out the right answer. And that would be a gnarly way to do this. Yeah, sounds not good. All right, so let's talk some more Unix stuff. So I have a number of things I want to talk about over the remainder of the course, about Unix and how Unix is set up and things related to working in Unix and so on. And so the order of these may not be particularly profound, but I want to start by talking basically about files and systems of files. So files and file systems. And so on a Unix system, there's a command you can use, which is df. And df gives you information about your file system. It's information about disks, but they're not actually disks anymore. But for example, if I say df, I see a number of things pop up here. So one thing I see is this thing /dev/sda. this is a hard drive. So this is a pretty basic terabyte solid state drive that I use for storing, you know, larger amounts of data. And it says mounted on /HDD. So if I go to my home directory, the root directory /, I can see all these different files underneath here. Well, one of these is a directory called HDD. And if I move into that HDD directory, I've got, you know, a bunch of files sitting in there. But in fact, those files are sitting on this physical device, this terabyte solid state drive sitting inside my laptop. Now I have another device. This is a high-speed solid state drive. It's only 250 gig. And that says it's mounted under /. So if I go to my root directory, it looks just like, you know, any other directory, but most of these files are actually stored on this particular physical device, this very fast solid state device. And so, sorry, this one. So this is, you know, cryptic code ending with P5. This is same cryptic code ending with P1. These are different partitions on that same fast device. And so /boot /EFI is a directory that sits in part of this, and / is a directory that sits in part of this. But if I happen to go to /HDD, it switches over to being on this other device, this slower drive. And so from a user perspective, when we're sitting in Linux and we're moving around our file system, we just see a tree, right? We see a root, which is called /, and underneath that is a directory called home and boot and etc and bin and so on. And underneath home, there's Nick, and there's, you know, some other user. And under etc, there's a password file. And under bin, there's ls and who, and so on. And we just see, you know, this tree of files. But the way you set this up, as an administrator, I could, for example, set this to be on a different device. And this /HDD, which has files and other stuff, this could be on another separate device. And as a user or as a program, we don't really care about these distinctions. But as an operating system, if somebody says, okay, I want to open a file under /HDD/files, it needs to know, oh, okay, /HDD, that's on this hard drive. So I need to go to the directory information on that hard drive and figure out where the file is that the person's asking for. So this is transparent to us, and it's transparent to our programs. But if we add something into our system, if we pop in a flash drive, for example, it will create a new entry in this table, and the system will have some way of getting to that device. So I can mount an external backup drive. And now if I do a DF, I've got this new entry. Well, this is a network drive. So it's on this IP address, and it's mounted under /media/nick/external backup. And if I go into that particular directory, I'm actually accessing a drive that's sitting on another box behind me. And then if I unmount that, that'll go away. All right, so we have this basic hierarchy of directories, but they can be split up over different devices. So that's good to know. And we can specify in this system file called fstab, file system table, we can specify what we want to happen to different physical devices. So this is a unique ID for that slow terabyte drive I have. Every hard drive you buy has a unique ID sitting on it from the manufacturer. And I'm saying, hey, if you see a device with this ID, mount it under /HDD. ext4 is the type of file system. So that's a standard file system for Linux. When you see this ID, mount it under /. So that's that fast solid state drive and so on. And down here is the information for that network drive. All right, so that's a little bit of backstory. And again, usually we don't have to worry about that too much. But those devices are sitting around in the background. All right, so let's go into a directory. And let's make a subdirectory under there. And we'll make a deeper directory under there. All right, so we know we can say pwd to see what my current directory is. So /home/nic, that's my login directory. I made a directory called work. Underneath that is a subdirectory and then a deeper directory. And inside here, I have a file called haha. So I can say vi haha, and I can edit this file. I can say cat haha, and I can look at that file. Now, if I move up one directory level and I say cat haha, it says no such file or directory. And if I do ls, I'm in this directory called sub, and there's nothing in there except this subdirectory called deeper dir. So sometimes I can say cat haha, and it knows what I'm talking about, and sometimes it doesn't. And in 121, if you're on a CTEX server and you want to run something in your current directory, you usually do this // and the name of the file. So there's two different ways of specifying a file on a Linux system. There's a way where you can just say something like haha, and then there's a way where you could say something like /home/nic/work/ something. And the main difference is, this specification begins with a /, and that / is this. It's the root of the file system. And when I say /home/nic/work, I'm saying, okay, start at the root, find a directory called home, find a directory under that called nic, find a directory under that called work. And so this is called an absolute path. If I don't have a / in the beginning, this is called a relative path. So a relative path is a file that you specify relative to where you are right now. So I'm in this directory right now where there's a file called haha. I can say cat haha, and I can see what's in that directory. But if I'm in a different directory like sub and I say cat haha, it doesn't find it, because without anything in front of this, it says, look in my current directory for this file. Now I can specify a relative path from here, like deeper dir /haha, and it will find my file. Because sitting in my current directory, this says, look for a directory in my current location called deeper dir, and there is such a directory. And then in that directory, look for a file haha. But if I'm not sitting in this directory, like if I'm sitting under my work directory and I say cat deeper /haha, it's not going to find it. So most of the time we're using relative paths. when you want to edit a file and I say vi main.c, right? I'm creating a file in my current directory. But sometimes we actually want an absolute path. And so if I use an absolute path, I could be sitting, you know, anywhere. I can be sitting in my main directory, but if I say vi/home/nic/work /subdirectory/deeper_dir/haha, doesn't matter what directory I'm currently in, because this is not relative to my current directory. This is absolute. And this will get me to my file. So everybody got the difference between those, absolute and relative? And so there's these special directories. There's dot and there's dot dot. And dot is an abbreviation for your current dir. And dot dot is an abbreviation for your parent directory. And so those are also relative, right? Dot is my current directory. So if I'm sitting here under home nic, dot means /home/nic. If I'm sitting under home nic work, dot means /home/nic/work. So here, if I say ls dot dot, that says show me what's in my parent directory, which is home nic, and that'll show me that directory. If I'm sitting under home nic and I say ls dot dot, that'll show me what's under /home, which is all of the directories under home. So that's absolute versus file. So dot is useful, for example, on the CTEX server. When you want to run a file in your current directory, you say dot / in the name of your program, ./a.out, for example. Because on CTEX, your user accounts don't include your current directory in the path. And so if I just type in the name of a file, it doesn't find it anywhere. Now, if I'm sitting under, you know, home/nic, I could say /home/nic/a.out, but that's a lot of typing. So it's easier to just say ./a.out. That's the main case. There's also commands like the find command. And find is a command that looks for files. And so find, the first argument should be where it should begin looking from. So I can say find /bin name star, and it'll show me every file under the bin directory, including subdirectories. There don't happen to be subdirectories under bin, but I could say find /-name star, and that'll show me every file on the system, including the ones under subdirectories and so on. So if I want to do a search starting in my current location, dot's a really useful way to do that. So I can search for every C file starting in my home directory and see all the .c files. We'll talk about find more later. Later, we will talk more about find, about that. But it's a good command to know. All right. So two ways of specifying files, and there's dot and there's dot dot. So next thing I want to talk about is how these files exist inside Unix. Right, a big part of what any operating system does is it gives you access to files. It lets you specify a file by name usually and get to its contents, whether to edit it or compile it or pull text out of it or whatever. And, you know, we refer to files by name because we're humans and that's what we do. And if I do an ls-l, I get some more information about my files. So main, main2, and main.c, this dash in the beginning says those are just files. And these are the permission bits. That's what we use change mode to affect. And this is the owner of the file, that's me. This is the group the file belongs to, which is also my group. This is how many bytes are in the file, 234, and this is the date and time of the last update to the file. And there's the name. Now sub is a directory, so this first character is a D. And if I look in sub, I see one file, but remember, ls by default doesn't show hidden files, which are things that start with a dot. So if I do an ls-a, I see there's actually 3 files under here. That's that 3 right there. So if I put a 4th file into sub, oh, I lied. Okay, there's still a 3 there. So that's something else. Never mind. All right, so these are the names that we use when we use fopen, or, you know, a command like cat or vi, which uses fopen. Those are the names we use, or our programs use, to get to these files. But those names are not what's used inside the operating system. So inside Linux, there's something called an inode number that uniquely identifies each file. And so if I say ls-i, I get this number next to each file name. That number is an internal index that's used to access a file. And we don't normally mess with these ourselves, but if we were writing code that wanted to, you know, take a file and access it on the hard drive, for example, directly, we could use these numbers to find out the information about this, such as where is it stored, and so on and so forth. And I bring up inodes for a few reasons. The first is to note that inodes are unique to a device, but I believe they get replicated from one device to another. So inodes are particular to a physical drive, for example. And if I plug in a USB drive, I might see things with the same inode number on them. So this is related to the question of links. Oh, and by the way, if we do an ls-a for all and I for inodes, there's inode numbers associated with dot and dot dot, right? This is just a directory. This is another directory. This is the directory sitting above us, so /home/nic. So if I go into home nic and I say, show me what's in this directory, there's a directory called dot with an inode 5111810. Well, that's the same inode as dot dot in the subdirectory. So this dot dot and this dot are exactly the same file, which they should be, right? Because if I'm sitting under home nic work, dot dot should refer to home nic. If I'm sitting under home nic, dot refers to home nic. All right, so links come in when, for example, you have some file that has information in it that maybe you want to access from multiple locations. Maybe everybody wants a copy of some file, and we can make a copy of the file by using the cp command, but that takes up space on the disk. And so, for example, let's go back into our work directory. And let me get rid of all of this. So let me make a file. All right, so here's my file, and if I look at the inode numbers, it's got this particular inode number. Now, if I copy file to file 2, file 2 has the same contents as file. That's what copy does. But if I look at the inode numbers, these are different files. This is an inode ending with 712. This ends with 589. So totally different creatures. And in particular, if I edit file, let's say I add some more stuff to it, and then I look at file 2 has not changed, and it shouldn't change because it's a different file from just plain old file. So sometimes it's more useful to have something else that refers to the same file instead of just making a copy of it. So this is what a link does for us. And so there's a command called ln, that means link. And we're going to put this switch -s, which means symbolic. And then we're going to list the old file, the file we're linking to, and then the new file, the thing we're trying to create. And so I can do something like ln-s file, and I'm going to make a new file called copy. All right, well, now I've got a copy in here, and if I cat copy, it's got, you know, the same thing that file had. Here's the cool part. If I edit file, let's go ahead and just make this a single line. And I look at copy, copy has changed also. So it's not really a copy of the file, it's another reference to the same file. And if I were to edit the copy, I can say this is the copy. Well, now if I look at the original file, that's been edited also. So links are different from just copying with a CP command. A link is a new pointer to an existing file. And if I do an ls-l, this becomes clear because now if I look at copy, it's got an L in the beginning instead of a dash or a D. That means it's a symbolic link. And it says copy arrow file. And it's saying, hey, this is really a reference to the thing called file. And it's got a different timestamp, right? This was created at 11:38, whereas file was changed at 11:39. It's also got a different size. This link only takes 4 bytes. What are the 4 bytes? FILE. But now, you know, if this, yeah, go ahead.
What would happen if you removed file?
So if I remove file, copy is still there. It's still referring to file. But if I try to look at the contents, it'll say no such file. Because it's referring to something that doesn't exist. Now, if I edit file and I put something in there, and now I cat copy, it'll show me what's inside file. So it's a pretty uninspired action, right? It's really just a shortcut to a file with this name.
Like the annoying shortcuts that programs always put on your desktop in Windows.
Yeah, exactly. Exactly the same idea. So if I copy to my parent directory, and I go up one directory and I do an ls-l, there's copy. And if I look at the contents, it's the contents of the file. All right, so this can be useful for a number of reasons. One is if you simply had, a file that lots of people wanted access to, you could create multiple links to that file and not have to actually, make physical copies of it. So if this is a big file that's, gigabytes in size, we could simply have different references to it. Another way that this is useful is for shortcuts. So a lot of times I work with this directory called files/useful commands, and I just have a shortcut called useful commands. So if I just say current directory into useful commands, I'm actually in this subdirectory called files/useful commands. The other thing that links are useful for is, for example, if I say vi, it says I'm executing /user/bin/vi. Well, if I look under /user/bin, vi gotta go way up here. Vi is actually a link to /etc/alternatives/vi. And if I look at etc alternatives inside here, vi is a shortcut to user bin vim.tiny. So if I wanted to change vi for everybody to become some other program, I could just change this link, and then when someone says vi, it'll go to this file and that'll link to some other file. Did I spell seek and destroy wrong? D-story, okay. Thank you. Yeah, so usually when I'm doing this, I just do seek and I hit a tab, but there you go, secret command. Seek and destroy is how I break my connection to students' GitLab repositories after the school year is over. It goes through my GitLab repo and looks for any projects that I belong to that aren't mine, and it'll remove my membership from them. So, and that's just a big bash script, which I can't show you because it has my private token in it. All right, so we can create these symbolic links. And this is really just kind of exactly what you see is what you get. It's just a reference to something called file. And I can make this more nuanced. I could say, for example, let's link /home/nick/useful commands /seek and destroy SD. And now I have a file on here called SD, but it's a link to this whole thing, which I've specified with an absolute path. Right, so this is a relative path again, so this will only work in my current directory, whereas this is an absolute path. And so even though my SD is sitting inside HomeNick work, it refers to a file in a totally different part of the directory tree. And if I do an ls-i, each of these links has its own inode number. And the inode number is file ends with 580. The inode number of this link ends with 589. It's a different file. All right, so this is a symbolic link. And these are the most common links that are used today. This has changed over time, but right now this is the link most people use. And it's nice because it's just based on names, which means that, you know, if this useful commands directory was on a different physical drive, doesn't make any difference, right? When I access SD, it will look for this path, right? And whatever devices these are on, it will still get to that file and it'll execute this command. So there's an alternative to this, which is what we call a hard link. And a hard link, we just don't put in the -s switch. We just say ln for link, old, new. And this becomes a link to that old file. So let me go back to just my original file and let's create a hard link. So I'll link file copy. And now if I do an ls-l, there's a copy, there's a file. And in this case, there's some differences. First of all, they both show the same file size, 11 bytes. They both show the same timestamp, right? So right now it's 11:48, but file was created 7 minutes ago. Even though I just created this link for copy, it says that the last update time was 7 minutes ago. And in this case, if I remove file, my copy is still there. And I can create multiple links. And now I've got copy file, file 2, file 3. They all have the same timestamp. They all have the same size. And in fact, they're all exactly the same file. And if I do an inode number, they all have exactly the same inode number. So these are really 4 references to the exact same stuff on disk. And that's different from a symbolic link. A symbolic link is something that refers to the name of a file, whereas these hard links refer to the actual inode of the file. And for all intents and purposes, they really are that file. And so here's one way to look at the difference. So our disks aren't round anymore, but I'll draw a round disk anyway. So we have our disk drive, and you know, we've got files stored on here in sectors and so on. And so there might be some file which is stored right here. So those are the parts of the hard drive where the file is stored. And with some symbolic link, there's somewhere else on the hard drive where this symbolic link is stored. And the contents of this say, hey, get me to, well, they actually point to, right, what's stored here is actually the name file. And so to access this symbolic link, we find where its information is on the hard drive, we find the word file, and then we look for a file with that name. But with a hard link, here's some spot on the disk where our file is stored. Well, copy refers to exactly the same stuff on disk. So it's really a reference to exactly the same area of information on this physical device. And you can tell that because the inode numbers are the same. So when I remove copy and I look at file 3 is still intact, right? So here's an interesting detail about the remove command. When you say remove, it does not necessarily delete the file from the drive. What it does is each file has something called a reference count, something that says how many things are referring to the same inode as this file. So if I just make a plain old file, right, it's got a reference count of 1. If I make a hard link to a file, the reference count of the original and the link will be 2, saying, hey, there's 2 things referring to the stuff that this points to on the disk. When I made 4 hard links, this reference count was 4 for each of those. When I deleted one file, the reference count for each of these went down to 3. And if I remove file, now the reference count is 2. So the remove command actually reduces the reference count by 1. But then it has this additional behavior. If after doing that, the reference count is 0, then it marks the file as deleted. So I can remove file 3, and I can still see the contents of file 2 because the reference count is 1. But now if I remove file 2, internally, the reference count of that dropped to a 0, and it said, okay, I'm going to delete that file. And so now it's gone. So that's how hard links work. And hard links, like I say, they're not used very often anymore. One of the reasons is a hard link does not work across devices. So if I have a file on my hard drive and I try to create a hard link on my flash drive, it won't work, because hard links are keyed off of inode numbers, and inode numbers on my flash drive have nothing to do with inode numbers on my internal hard drive. But they are still an option, and so you want to know about hard links as well as symbolic. And there's manual pages for all of this. I can do a man on the ln command, makes links between files, and you can read all the details of this. And I can do things like, make a subdirectory that links to myself. So I can say, let's change into the subdirectory. And now I'm in my subdirectory. And I can, do this multiple times. And now I'm in this, subdirectory under my subdirectory under my subdirectory. But I'm still in the same directory, because this link is pointing to my current directory. And this becomes a concern, for example, if you're doing something that traverses directories. If you had a program that tried to move through every directory and subdirectory in your system, it could get tripped up when it encounters something like this, because if it sees a subdirectory in here called sub, it might start traveling down that and get into this directory, and it looks and it sees a directory named sub, and it might just keep going down that rabbit hole forever. And so a lot of utilities that traverse directory trees have special options that affect how they deal with symbolic links. So these are just things to know about. All right, questions about any of that? I promised you a kind of random collection of topics for the lecture, so I think I'm delivering. So if I remove copy, right, this goes away. We're back on our hard drive now. And file in my directory structure has an inode number, which somehow gets me to this area of my hard drive. And stored in the magnetic material of my hard drive between here and here is the contents of my file. And the reference count to this inode that references that is 1. And so if I say remove file, it reduces the reference count to 0. And file gets removed from my directory information. And now when I say ls, I don't see file anymore. But here's the $100,000 question. What happened to this information that was stored in the hard drive when I delete my file? What's the fate of that information? It gets marked as deleted. What else happens to it? Yeah, it's still there. It's just not reserved anymore. But unless you do something special, something more than just remove, this information is still sitting on the hard drive. At some point, it'll probably get overwritten, because when it's marked as not in use, if something else needs space on the disk, well, it might use this space and write something else on there. But if you delete a file with, a simple RM command, the contents of that file is probably still sitting on the physical device. And this is important to know. So if you're donating a laptop to Goodwill and you want to clear out your hard drive and you just remove all the files by hitting the delete key, you actually haven't removed that data from the hard drive. And it's very easy to take a hard drive and just start looking at this data, and you can get back the contents of the files that were stored before they were deleted. So this is nice if you want to have an undelete feature. And there's undelete programs that will basically go into your hard drive and look for what is the remnants of a file that was just deleted and create a new file that points to that area of the disk and gets your files back. So that can be a nice feature, but it's also a problem if, you've got personal information on a device and you try to delete it by, hitting the delete key or something, and then hand that drive to someone. Well, they can probably get the information back. And yeah, permanent delete on Windows, I think just puts it, does not put it in the recycle bin, but I don't think it actually overwrites. And if you want to avoid this, you need to do something with the bits that were on the disk. So a typical thing to do would be to overwrite them. So for example, you could take the contents of the file and you could change each character to an X. And then if somebody recovers the information on the disk, they're just going to see a bunch of X's. And so that, there's all these different shred utilities that'll do exactly that. They'll delete a file, but before they remove the reference to it, they'll change the contents to some pattern that has nothing to do with the original contents. But even that is not always good enough. So if you have a physical medium that's magnetic, right, effectively we code information by storing these magnetic dipoles, right? So we make a little magnet, and north can point up or it can point down, and maybe we use this for a 0 and this for a 1. And by controlling the magnetization of each piece of our hard drive, we can store binary information. And so maybe you have, something like this. So 0, 1, 0, 1, 1, 1. Maybe that's the piece of information that's stored. And maybe we want to safely delete that. And so we're going to go through and we're going to change all the polarizations to look like this. We're going to write a bunch of zeros. But the reality is, if you take this hard drive and you pull it out of the computer and you bring it into a laboratory, you can probably get back this original information. Even though all of these things have been flipped to store zeros, because taking this and changing it to that leaves a different signature from taking something which is storing a 1 and flipping it to a 0. this is going to be more strongly polarized in that direction than this, which started off pointing down and now is pointing up. And so people who do digital forensics can do this. They can take a hard drive and examine the physical platters that make it up, and in many cases recover the information that was stored before it got overwritten. And so how do you counteract this? Well, maybe, you write a bunch of zeros, and then you write a bunch of ones, and then you write a bunch of zeros, and you write a bunch of ones, and you do that a few times and really try to jumble it up. And so there's standards. There used to be something from DoD called the Orange Book, and it was a standard for the requirements for securely erasing classified information from drives. And it called for, certain alternating patterns to be written in some succession, and they had to be written X number of times, depending on the classification level and so on and so forth. And it all gets really hairy really fast. The punchline to remember is that, security is largely an illusion. We talked about cryptography in 215 and secure transmission, and that's an illusion. And certainly deleting a file does not, remove it. And unless you physically destroy the drive in a way that makes it impractical to put back together, for example, grinding it into powder, there's pretty creative ways to get back information. I remember when the embassy fell in Iran at the end of the 70s, people shredded the documents on their way out of the embassy. And the Iranian government was able to just reassemble those shreds. Took a long time, but they went through and meticulously pieced them back together and were able to recreate the shredded documents. So that was before cross-cut shredders were popular. SSDs use a different technology, but I suspect there's a similar effect, because when you write a 1 to an SSD or a 0, I don't remember which, it physically damages the material. It takes away a little piece of material and changes it in a way that's permanent. And this is why there's a limited number of write cycles. And so I suspect there's some fidelity in the information you could recover from looking at how that damage has been done. But I haven't looked at any papers on that. I'm sure you can Google security of deleting files on SSDs and find some interesting stories. So yeah, security is largely just making it so difficult that it's not worth it to somebody to try to figure things out.
That's why you might have like a garage door opener that's got a four number key code.
Yeah,
That works fine for your garage door because not very many people are going to be next to your garage door. But for your computer, that doesn't work because there's
exactly.
potentially millions of people that are going to be next to your computer.
Right.
And have plenty of time to get in.
Yep. And I'm going to notice someone standing outside, every day for 6 hours with a garage door opener staring at my door. But we don't notice this on the computer. Cool. All right. So that's all I got for today. So next week, I want to start talking about this dialog command. This is what we're going to use in PA5, which we'll talk about next Thursday. But Tuesday, I want to start talking about dialog. And then we're going to keep working through different pieces of Linux. I want to talk about processes and give you some of the Unix side of that, and then also look at processes from a C perspective. We'll look at some more things we can do in scripts around executing commands and controlling their input. We'll look at some other utilities like curl and find and awk and sed and gprof, and we'll talk about regular expressions. And those kinds of things will probably take us out to the end of the course. We're going to lose most of a week over Thanksgiving. And we're finishing up week 7 now. So we've got 4 weeks minus Thanksgiving. So we're in good shape here, but we'll continue with all of this on Tuesday. All right, so hope everybody has a great afternoon, and I will post this recording after class, and I will catch you all next time.